Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Claudio Maccone, who's come across to us from Italy today to speak to us about the Drake equation and extensions of the Drake equation. Claudio obtained his bachelor's in maths and physics at the University of Turin in Italy. And then completed his PhD in mathematics at King's College in London. He worked for the majority of his career at Alenia Spazio, the Italian space agent, the Italian space company, working on a project that he spoke to us about last year, which is using gravitational lensing to affect astronomical instruments, observations. Claudio retired from that in 2004, allowing him to devote more time to particularly the SETI question. And he is currently a technical director at the International Academy of Astronautics. And today he is going to talk to us about a paper that has just come out in Acta Astronautica, where he examines the statistical probability of inhabited planets close to us and spread throughout our galaxy. So if you'll join me in welcoming Claudio.
Thank you very much. I hope you can hear me well. Sorry about my poor English. Well, I'm really glad to be here. Last year I gave a talk about space mission to use the sun as a gravitational lens. This seems technical, but actually it would be a great achievement because we would possibly get in touch with extraterrestrial civilization much better than we can as long as we stay on Earth. Now, this year my talk is somehow different. I would say more wide spectrum. Basically, as Andrea Brown said, I am a mathematical physicist, so I like to play with the equations. And since we are now at the SETI Institute, in the temple of SETI research, that is the best institution in the world where scientists try to get signals from alien civilizations, I think a talk like this could fit with what we might possibly expect with a contact with someone else. So at the moment, this is just a bunch of equations, no more, and to publish papers that I'm going to mention in a moment. But in my opinion, this might possibly develop into a large computer code. And the goal of this large computer code would be, if you let me use Carl Sagan's words, Encyclopedia Galactica, that is a large collection of data that we have acquired over, I would say, the centuries, that might help us to understand better what we might find when we get in touch with some alien civilization. Of course, this is going to be mathematical. This is why my title, I'm afraid it may be somehow scary, is about the statistical equation for Habitable. That is, what we could possibly expect by using statistics about other worlds, habitable, that is, where we might possibly live. And beyond that, I am going to face, again, with the language of statistics, an old problem that I'm sure most, if not everybody of you knows about, that is the question of the Fermi Paradox. That is, given the size of the galaxy and the age of the galaxy, it turns out very easily that an advanced civilization might be traveling around and colonizing the whole galaxy in a comparatively speaking small amount of time. Something like a few million years would be enough for a civilization to colonize the whole galaxy. So the question is, since we have no proof so far that they came over here, let me say, no scientific proof. Of course, there are many hints that this may have happened I know, I would even share that, but that's another story, and I don't want to run into questions of, science fiction novels, adventures, whatever. So since we have no scientific proof that they know about us and they came here already, well, the question is, are we alone? And the question was asked by Enrico Fermi at Los Alamos in 1950 during a lunchtime conversation. So this is, I think, interesting because it shows that lunchtime conversations sometimes can be even more productive than official lectures and meetings and boring procedure. Let me use this term. Well, this is not surprising because the lunchtime conversation is when the hidden part of us comes out. You're sitting with some friends and you talk freely, you are not afraid of being fired, anything like that. Okay, so that was the story of the Fermi Paradox. And today I would like to tell you about all these topics. Unfortunately, I have to say with some mathematics, but this is not going to be a mathematical lecture. My goal is to explain these results in an easy and understandable language. Thank you. So let's go over to the first slide. Well, may I suggest two reference papers that describe exactly in a scientific fashion what I'm going to talk about today. The first such paper is entitled SETI and SE. SE is the statistical equation for habitables, intending habitables for man. They could be habitables for aliens, but then they may have different characteristics. We will see that at the end of the talk somehow. So anyway, the first paper was published well, this is ridiculous, in 2011. This is simply because the journal publishes with future dates. So it goes over already into the next year's first issue. Anyway, the journal is Acta Astronautica. For those who may not be acquainted with this, Acta Astronautica is the journal of the International Academy of Astronautics, to which I belong. And the International Academy of Astronautics is really a large association of about over 2,000 people who are basically experts in space flight and space-related topics. SETI is a space-related topic, of course. And so this is the first paper that I would suggest for you to read if you want to know about the equation, the proof of the theorem, and all that. And then there is a second paper called the Statistical Drake Equation, again published in Acta Astronautica this year. These are the pages. And this is again the full set of mathematical proofs of the equation that I'm going to explain in easy terms today. Good. So let's go over to a sort of sketch of my talk. I'm sorry, I'm going to move around because I don't like staying at the podium all the time. I feel it's less formal and more friendly way to talk. So my talk is basically divided into three different parts. Part one, the statistical Drake equation. This is the best place in the world to talk about this because Frank Drake, of course, is the president and honorary chair of the SETI Institute. And let me confess that Frank and I have been in touch about all these things since 1987. So I had the honor and privilege to meet Frank Drake for the first time in 1987 back at a conference. It was the second bioastronomy conference held in Hungary. Balatonfüred was the place on Lake Balaton. And if you wonder why it had to be held in Hungary, the reason is extremely easy, because at that time the Cold War was still going on. And we Western scientists were allowed to go there, but they, Eastern scientists, were not allowed to come here. So we had to go there. It was a great conference. I met with other great names in SETI business, for instance, Kardashev and so on. And Jill Tarter and Frank Drake were there. So that was my first contact with Frank. And I have learned so much from him, honestly. I regard him as the person who influenced me more than anyone else in my scientific life. Second part of the talk. This is about the statistical Dole equation. What is that? Well, Stephen Dole, unfortunately is no more with us, was working at the Rand Corporation. And in 1964, he published a book by the great title, Habitable Planets for Man. The title tells all. Great vision of the future expansion of humankind in the galaxy. Now, if you read that book, there are a number of technical details about how planets must be in order for us to live on the surface of those planets. So it's not just a matter of having an atmosphere, having breathable air and all that, there is much more. Of course, so first of all, the gravity must be comparable to ours. But that's not just the whole lot. You have, for instance, the tilting axis, the tilting of the rotational axis, that must be not too different from the tilting that we have, 23 degrees, you know, because the tilting gives the intensity of the seasons. So if it's different, we would have very, very hot season and very cold winters and all that. So if you go through that book, it's really well described. I would say that that was really the first book about planetary science, much ahead of the time when this name became known as we know it today. But the key point in the book, in my opinion, is chapter 5, where it gives one equation. And that is the Dole equation. That is to find out how many planets habitable for man could possibly exist in the galaxy. We'll check that, but this is the key point in the story that I would like to stress. Finally, third part. The third part is the Statistical Fermi Paradox. That is what I already mentioned, this discussion that went on at Los Alamos National Laboratory in 1950 between Enrico Fermi and other scientists. And the conclusion is that here we find the statistical version of the Fermi paradox. Good. So let's go over to the statistical Drake equation. Well, it's very easy. Frank Drake, in 1961, published a famous equation that is intended to give the number of communicating civilizations existing in the galaxy right now. This number is obtained by multiplying 7 factors. And of course, Frank gave numbers to each factors, even if in an arbitrary way, and then he derived the number of civilizations. Now, what they did in 2008 was to generalize Frank's equation by assuming that each factor is not just a sheer number. That is, with all respect to Frank, this is too simplistic. Each factor is a probability distribution. That is, a mean value plus or minus a standard deviation on each side. This is more scientific of a description. But of course, that brings a number of questions. For instance, what is the right probability distribution? I will answer this question in a moment. But now you've got the basic idea of what the statistical Drake equation is. So the point is that there is an error bar associated with this value. Well, let me just point out 2 practical equations. These are the only equations that I'm going to show in the talk, but I wanted to point them out because they are key for the rest of the story. The first equation is the LOGNORMAL probability density function. PDF stands for probability density function, and this is the equation. Of course, the independent variable x ranges only for positive values, and that makes the difference, for instance, between the Gaussian or normal distribution that ranges from minus infinity to infinity. It's a completely different story. This is for positive variables only, which is what they are in the Drake equation. So we cannot apply Gaussians to the factors of the Drake equation, because the Gaussian applies to real number from minus infinity. And the following equation is a probability density function that I discovered after that, and gives the average distance between any 2 nearby civilizations in the galaxy. Good. There is one more constant that will appear in the rest of the talk. This is this capital C constant. That depends only on the size of the galaxy. So, of course, it's the same for all consideration about extraterrestrial in this galaxy. But if we want to find out a mathematical theory about extraterrestrial, for instance, in the Andromeda galaxy, which is the nearest one, M31, then, of course, we have to change this number. So, again, this theory is the mathematical theory that potentially applies to all spiral galaxies. You just change the numbers accordingly. Now, here I would like just to point out a crucial fact about our own galaxy. That is, if you assume, as we had to assume so far, that the extraterrestrial civilizations are uniformly scattered all over the volume of the galaxy, then there is a very neat relationship in between the assumed number of civilization, you see from 0 to 100,000, 200,000, and so on, up to 1 million civilization, and the average distance between any two nearby such civilizations. That goes up in light years from 0, increases to 150 light years, 500 light years, and so on, up to 2,000 light years. So this is a simply called a cubic curve, because of the volume, clearly. But the key point is that if you just consider the size of the galaxy and nothing else, which is well known, you get this curve relating in a precise fashion the number of assumed civilization and the distance, the average distance in between them. Okay? Good. Let's go ahead. This is the classical Drake equation. This is from Drake, of course. And let me just say very briefly what the 7 factors are. You probably know about that already, but let me just summarize very quickly. So the capital N on the left is the number of communicating civilizations in the galaxy right now. N, it would be N sub S, but to make it clear, I just wrote NS. NS is the number of stars in this galaxy. This is pretty much well known. It is about 200 billion, someone say 300 billion, someone say 400 billion. Of course, this is a statistical estimate. So once again, statistics is absolutely crucial in this thing. You cannot pick a number of, the exact number of stars in the galaxy. Nobody knows about that. Nobody can count, of course. So this is the first number. So as to say, this is the big number. Then we have the next number, which is the fraction of stars that have planets. Now, the fraction of stars that have planets is not exactly well known, but we certainly know much more now than we used to know a few years ago, because now we know about nearly 500 planets. The point is that these discoveries are, let me say, biased, meaning that the technology that we use today in order to find these planets are basically favoring the discovery of big planets like Jupiter, Saturn, and all that, and not the discovery of smaller planets like the Earth and so on, that still has to come. So we have certainly a partial view of the story at the moment, but certainly we know much more now than we used to know 15 years ago. So nobody knows about that, but I am not going to stick any number about that. Next, the next factor is the number of Earths, so as to say, for each planetary system. Now, for our planetary system, this is supposed to be 2, because the Earth and Mars are habitable planets in the way that we know them. Of course, there may not be, or there may be life on Mars in very primitive forms. We don't know about that. Maybe there has been life on Mars in the past. We don't know. Next factor. Well, let me stop here, because these 3 factors are basically astrophysical parameters and astronomical parameters. Okay, so these 3 numbers in the Drake equation summarize our knowledge in the field of astronomy, astrophysics, space sciences, and all that. But now we come to a completely different story. The next factor, FL, is the fraction of all that is suitable to host life. Life, as we know it, of course, we may be very limited in this definition. So, in plain terms, the 4th factor is essentially the Darwinian evolution. That is, the question is, assuming that there are so many planets on which life can be born and grow, on how many of them that really happens? Now, of course, life can be understood in different senses. In my understanding of the story, this goes from DNA, so small cells and all that, up to animals, but not to humans. The difference is that animals live basing themselves on instincts, whereas humans have reason. So that is, in my opinion, the basic distinction. But of course, we could talk philosophically for plenty of time about that. So in this factor is the full Darwinian evolution on Earth as it occurred. The next factor is Fi, the fraction of all that finally bears intelligent life. What does intelligent life mean? Well, once again, in my understanding, this means Homo sapiens, so, I don't know, 1-2 million years ago, up to now. Meaning that those creatures were already intelligent enough to handle fire and all that, whereas animals cannot do that, right? But again, we could discuss endlessly about this. I'm rather pleased to say that, in my opinion, this ends in the year 1864. Now, we are in America, 1864, that was the time of Civil War and all that. But in Europe, especially in the UK, there was a great physicist, James Clerk Maxwell, who in the year 1864 published what we now call the Maxwell equations. Now, this was a turning event, pivotal event in the human history, in my opinion, because we would not have TV, radio, satellites, cell phones, anything, if Maxwell had not written down this fourth set of equations. Now, you may say that I'm giving a parochial talk because I'm basically a mathematical physicist, so I like this kind of stuff. True. And yet, sorry, but this is the reality. We would not have the modern world without those equations. So that, in my opinion, is the turning point, and this is where the next term starts. Fc is the fraction of all those that leads to communications. And communications among different stars at the moment can only occur by virtue of electromagnetic waves, which is what Jill Tarter and Frank Drake and other people here at the SETI Institute have been doing since Frank started in 1960, right? So we are really in the right place for this kind of science and so on. And finally, there is the last factor. Oh my, this is beyond our reach. This is how long can a civilization that has reached that level possibly exist for? Nobody knows. Nobody knows. Let me just say something. What could put an end to such a civilization? For instance, an asteroid hitting the Earth. We are all living on Earth. There is no human living somewhere else at the moment. They live on the moon for a small while, but at the moment they are still here. So the conclusion is that an asteroid could put an end to our civilization right now if we were not able to deflect it or get rid of it. Another different possibility is that, who knows, a supernova might explode nearby. And you know that there is an awful lot of radiation going up in a supernova explosion. So we could really be fried, literally, in such an event. And so on and so forth. There could be other reasons. For instance, a rock planet. What is the hell of a rock planet? Rock planet is a planet that, for gravitational reasons, got rid of the original planetary system and it's following another path through the galaxy. Right? So if a rock planet would enter the solar system, you can watch the simulation. There is something to get crazy about, because all the planetary orbit would be disrupted, and so we would die for a different reason, but it doesn't matter. So this is the Drake equation, and the Drake equation has this fantastic power to summarize in a product of 7 factors 10 or more billion years of galactic evolution. This is the key point, the great point about the Drake equation. Okay, I want to go fast because I see the time is running fast. So anyway, the original thing had 7 positive factors, but we don't like that, so we replace everything by a random variable, and we call that the statistical Drake equation. So the statistical Drake equation is that thing. That capital pi means a product of 7 factors. Now, I denote by capitals random variables, just not to confuse them with ordinary algebraic things. Okay, so the first step is clearly, if you want to extend this story more than Frank did, is clearly to replace that by the upper limit, 7 in Drake's mind, by any positive number, it could be any number. So this is the first step, because it takes you over to an infinite, to a finite problem, that in the limit, and here is the key step in this problem, becomes an infinite problem. Now, let me tell you a bad confession, because I want you to get the feeling of what scientists really have to come to grips anytime they face a new problem. I lost 10 years of my life in trying to find the probability density function of capital N, supposing that we know the probability density function of each disabi for a finite number of variables. Oh my, this is an unsolvable problem. Or anyway, I was not able to solve it. Even if I start to simple, particularly simple probability distribution, like the uniform distribution, okay, which is a constant in between the starting number and the end number, but 0 outside, so nothing is easier than that. But even that didn't give me a neat equation for this thing. I had to go through Fourier transform, but it was not an easy thing. So I lost 10 years of my life about that, and I didn't know how to come out of this problem. Until, having had enough of this failed attempts, I just wondered what's going to happen when this thing goes to infinity, or approaches infinity, so it becomes infinity line. And that is the solution of the problem. Now, why is that? Because all science is built on the calculus. And the calculus, even if it is so customary today that the students know about that, is basically a step to the limit. There is always a limit. When you define a derivative, the derivative is the limit of the incremental ratio, you know. So this is the great point that some people forget about, and I did certainly forget for 10 years. We have to take the limit, and then the problem is solved in 2 lines. And here is what happens. First of all, take the logs of both sides. This is basic, because if you take, I took the natural log, but you could take the log in any base, it doesn't really change it. So you take the natural log of n, and this turns the product into a sum, of course. But then, when you look at these are new random variables. The log of capital Di are new random variables. So, it occurred to me that there is a basic theorem taught in any course of statistics called the Central Limit Theorem, which in loose terms states that if you have an infinite sum of probability distribution, and you don't care about which probability distribution is adapting to each term. That is, you make no assumption about each. But the point is that if you have an infinite sum of such things, then whatever are the input distribution, the sum, the overall sum, approaches the Gaussian distribution, or normal distribution. This is a fantastic theorem. This is the most important theorem of the whole of statistics in itself, because it explains why the normal distribution or Gaussian distribution is so common. There are so many different factors that we cannot take into account, but the sum of all that approaches a Gaussian. So if you apply that, now you can apply it, because here you have a sum, no longer a problem. Clearly, the conclusion is that the log of n approaches a Gaussian. So we have solved the problem. We just have to make one final step. If the log of n approaches a Gaussian, what does n approach? Well, this problem was faced for the first time in history in the year 1870 by the British statistician Sir Francis Gould, who was working at University College. He solved the problem, that is, he was able to invert the equation. And he found a new probability distribution that no one else had found before him, which is today called the LOGNORMAL distribution. Okay? And I gave you the equation just at the beginning. So this is the result that opens up the solution to a number of problems. Log n tends to the normal, and n, that is the number of Sionaling civilizations, is log-normally distributed. Wow, this was the real step ahead. Look, I hope you will excuse me if I'm being sincere. Of course, friend Drake knows about that, because you are not the first people I'm explaining this to. The first person I explained this to was friend Drake himself. Well, the story is that when I finally realized this, that is n follows the log-normal distribution, it was such an obvious result that I spent a few months searching the web for anyone else who could have found this result earlier than I. But I could not find anyone. So even if this is so obvious now that the proof has been achieved, it seemed that I was the first person to have discovered that. So I published that. And of course I spoke with Frank, and Frank agrees that this is the next step in the study of the Drake equation, because his Drake equation is the special case of my largest statistical thing, when all the standard deviation gets to 0. Okay, so this is done, and now we go ahead. The next point is, of course, the distance. Now, as I mentioned at the beginning of my talk, if we assume that the probability distribution is uniform, the distribution of extraterrestrial civilization is uniform throughout the galaxy, then clearly, since we are talking about volumes of space, the distance, the average distance between any two close nearby civilizations is a constant over the cubic root of capital N. But now we know that capital N follows the log-normal distribution. So the next question, mathematically speaking, okay, what is the probability distribution of the average distance? And this is what they found, that if you take a course in probability, they will teach you how to play with probability distribution. And this is what they found. And here is the result. Now, this is not log-normal. This is what Paul Davies called the Maccone distribution. But anyway, it's another probability density. They give you the equation in the beginning. Please have a look at this thing. On the horizontal axis, there are the distances from Earth in light years. So we start from 0, and for instance, we go up to 500 light years. And you see that this part of the curve is really on the axis itself. Now, what does that mean in terms, in the practical, easy term? It means that the probability of finding an extraterrestrial civilization in between here and 500 light years away is practically 0. And this explains why we have been doing SETI for 50 years and we found nobody. Because our radio telescopes, however large, have not the capability of detecting radio waves coming from distances above, say, 100 light years or towards 200 light years, if they are emitted with powers comparable to the powers that we use on Earth for telecommunications. So this trivial thing, this 0 in between 0 and 500 light years away, this is the answer to the failure of SETI so far. And this is, of course, the answer to the future also, because you see that if we can go beyond 500 light years, the curve raises up incredibly, and it reaches the peak around 2000 light years. Or, if you want to put it in plain words, the expected distance between ourselves and the next civilization, at least advanced as we are, should be around 2000 light years or more. And we just cannot reach that distance with our equipment so far. Conclusion. This is just what they said. We did not reach far enough. Next. This is part 2. So please forget for a moment about what they said about extraterrestrial civilization, which is of course the theme of the great equation. And consider the other problem, completely different in words, but not in mathematics. Completely different. That is, what is the number of habitable planets for man in the galaxy? That is, if you want to put it, how many Earths could possibly exist in the galaxy as far as we know? This is the second part of my talk. Now, as I said, I'm not going to go through the answer because time is running fast, but let me just mention this great book that I mentioned at the beginning. The book by Stephen Dole, Habitable Planets for Man, year 1964, and actually you can download it for free on the web now. So it's just a delight, really. You go through all that, and there are equations, but in my opinion, the key equation in the story is at the beginning of chapter 5, when he handles the problem of probability of occurrence of habitable planets. These are the 10 inputs and the output. The output is the first line, that is the number of habitable planets in the galaxy. And then there are 10 inputs, and this is the Dole equation. So, the number of habitable planets given by the multiplication of all that. Of course, this is the same story as the Drake equation. The only difference is that in the Drake equation you have different words and 7 factors. Here you have different words and 10 factors, but who cares? My approach considers an infinity of factors. And incidentally, if you want to have an engineering look at the story, let me tell you that even if you just confine to 3 or 4 factors, this is enough to shape up the log-normal distribution. Okay? So 7, as in the case of Drake, or 10 in the case of Dole, is more than enough to approach the log-normal curve for all requested needs. Good. So this is the statistical Dole equation, and then I don't repeat the full story because you know it already. The conclusion is that the number of habitable planets is log-normally distributed, clearly. So there is a mean value, there is an error bar. Let me give you an example, please. Here is the Dole equation with the 10 input numbers that he uses in his book. So I'm just translating his book into, of course I wrote a code, MathCAD code to prove that. So I'm just translating his book into an example of my theory. Then, the mean value of each input random variable clearly is the same as the input number. So this column here is exactly that column there, not changed at all. But then, in my theory, you have to give standard deviation, the sigma of all these 10 things. Now, I have no idea, honestly, what the sigma can be for all of these things. So, since this is just a numerical example for the benefit of showing how the theory works, I arbitrarily stick 1/10, that is 10% probability as each standard deviation, okay? Of course this is incorrect, but who cares? I'm talking about the mathematics, not about the actual number. The actual number will be given later by scientists who specialize in each field. They are the knowledgeable people. I am just here laying down the full mathematical structure behind the story. It's like, I'm sorry for the comparison, but when Isaac Newton discovered the law of gravitation, the important thing is the law of gravitation. Then all the trajectory of the planets, asteroids, whatever, have different numerical parameters. Fine. They will be found later. But the key point in the story is the law of gravitation. And here is something similar. I'm just talking about the mathematics, not about the details. So, here is the log-normal distribution. Now, on the horizontal axis, you have the number of habitable planets in the galaxy, according to Dole. And here you have the probability. Now, conclusion. The classical Dole equation, the classical, that is the pure product, no standard deviation at all, yields about 35 million habitable planets, that is 35 million Earths in the galaxy. My theory, which is of course the statistical extension of that, even with the same input numbers, the same mean values, yields 100 million. So you see, the moral of the story, the philosophy if you want, is that if you just open your mind to using statistics rather than trivial mathematical multiplication of 10 factors, then you get a much higher number of what you're looking for. For instance, in this case, Earth, habitable for man. So, you know, there is a difference between 35 million and 100 million, 350 times as much. So that comes only because, Stephen Dole did the mathematical analysis in the narrow-minded way. Had he done it in the open-minded way, he would have found that number exactly the same. In addition, in my theory, we reach a standard deviation of plus or minus 200 million. Now, we know, of course, that one such world exists, and it is our. But that extends upbound, the number up to 300 million. So the conclusion is that we are much more encouraged to search and to expect Earths around, because this is what statistics foresees. Distance. Now, again, the story is the same as for the direct equation, so I'm not going to repeat this. But let me give you the numbers, please. The distance in between two nearby Earths, according to the classical Dole equation, is 88 light years. According to the statistical theory, it's going down to 88, it's still 88 light years, but with an error bar of plus or minus 39 light years. Wow, this is good news, because we are just looking for Earth right now. As you probably know, the latest news in planetary detection are the so-called super-Earths. I'm sure you're familiar with that. Super-Earth were discovered very recently, 1-2 years ago. And of course, scientists are debating, whether they are similar to Earth or not. Let me just, for fun, tell you a sort of small sentence. Super-Earth, mini dinosaurs. And conversely, lower Earth, bigger dinosaurs. Meaning that I was, last summer in August, there was a 10-day conference about Super Earth in France at the Observatoire de Haute-Provence. And we were discussing about, not just about the Earth, but about the size of dinosaurs that could live on the Earth. Well, if the Earth is bigger, the dinosaurs might be smaller because the gravity is so much higher. So they have to crawl anyway, you know. And vice versa, if the Earth is smaller than the Earth, then we expect huge creatures. We don't know whether this is right or not, but in my opinion, that is worth being investigated statistically. That is, using again this trick that I used. Next talk, I hope. Okay? So anyway, again, this is encouraging because we are increasing the number of planets. So this is the distance of habitable planets, distance of Earth and in light years. So you see that something like 50 or so light years is the peak of the curve. Good. Let us reach the final part. Just 15 minutes left, and so this is the final climax of the story. Now, what we saw in the second part is basically a statistical equation for the average distance between any two Earths. What does this help us to understand? Well, it helps us to understand the so-called Fermi Paradox, which is what I described at the beginning of the talk. That is, okay, this is taken from an old-fashioned presentation of the Fermi Paradox. So please don't be surprised if here the number of stars in the galaxy is supposed to be 400 billion. It could be 300 billion, 200 billion, who knows. We are over there in the outskirts, of course. This is Edward Teller, of course. This is Enrico Fermi, and this is the Los Alamos Fuller Lodge cafeteria where the lunchtime talk, discussion took place. Again, for psychologists, there is plenty to study in this thing, because during a lunchtime talk, a new branch of science was created. So anyway, this is just the proof that they mentioned that if you consider the size of the galaxy, and if you consider the size of our spaceship as that will travel around, I'm not going to waste too much time on this. The bottom line is that in order to colonize the galaxy, a few million years, here 150 million years, would be sufficient. This is the key point in the story of the Fermi Paradox. Of course you can change the number, but that doesn't really change the argument itself. Now, 150 million years for a civilization to colonize the full galaxy is not a long time, because the galaxy has been living for at least 10 billion years, much larger time. So the question is, why didn't they come over here if they expanded throughout the whole galaxy? And since we have, as I said at the beginning, no obvious proof that they were here or they are around here, I would not go into the UFO story because that would bring me possibly out of science, and I am a scientist, not a science fiction writer. Okay. But anyway, forget about UFOs and all that. The real story is that we have no sign of any extraterrestrial civilization. So the conclusion is nobody knows whether we are alone in the galaxy or not. This is the Fermi Paradox. Now, this is just what they mentioned, and they could skip on it. Now we are going over to the Statistical Fermi Paradox. What is the Statistical Fermi Paradox? It's the extension of the classical Fermi Paradox, stating probability distribution rather than pure numbers. Usual story. Now, I had to base myself on a model of expansion of a civilization throughout the galaxy. And since here at the SETI Institute we have Bennett Shostak, who, with another author called Jeffrey Bennett, wrote a great book about life in the universe. I hope you have seen it. It's a big book, popular level, but not without equation. There are some equations. Well, anyway, in one of these chapters, there is the coral model of expansion of the galaxy. What does that mean? It means that, taking example from what corals do in the sea, you have a rock and you have a coral colony that expands in time over the rock. But the key point in the story is that it expands at the edges, not at the center. So the new guys in the colony are the frontier guys, the pioneers, so as to say. Okay? They expand outward, and so the whole thing grows up. And this is precisely the mathematical model that we assume here in order to analyze the statistical Fermi paradox. I had to assume a model, and I assume that. Now, let's see better what that means. It means that this is a V, it's not an O, I'm sorry, the word processor wrote it in a bad shape, but this is a V standing for velocity. The velocity of expansion of a civilization in the galaxy basically depends on three factors. First of all, capital D, which is the distance between any two stars suitable for that civilization. Now, please notice that here we are drawing the mathematical theory not only of ourselves and our future expansion in the galaxy, but also of alien species. We just have to change the characteristic of that planet that originates the species, and then the mathematics is already there in order to find out how they could possibly develop. Clearly, there must be different distance in between planets habitable for those guys and planets habitable for us guys. But that is in the game. Okay? So, the expansion speed is given by the distance, which we know already to be a probability distribution, over the sum of two different flights, the sum of two different times. One time is, of course, the time of flight. That is the time that those guys have to spend in the spaceship in order to move from one planet to the next. Now this, I would not regard as a random variable, because, at least in our case, we know what our spaceship are going to be, so we know the speed of those machines. Okay? So, this is a number that follows from the engineering of the spaceship, and they would not regard it as an unknown thing. It is a known thing. So there is no way, no interest in treating this thing as a probability random variable. But the other term, that has to be a probability random variable, because that is the time that is requested to a civilization from the moment they start living on that planet or in that new land to evolve up to the point that they are reached to make the next step, fly to the next planet. For instance, in the case of America, America was discovered by Europeans in 1492. Good. After 500 years or more, we have seen that the United States are the most important country in scientific language existing on Earth. Now, this is precisely what I'm meaning by this probability distribution. So I had to assume a probability distribution for that. Let me just show you that. Okay, I had to assume a probability distribution for the planet colonization. And my conclusion was to assume a log-normal once again. If you ask me why, well, because at the beginning of the talk I proved that the log-normal is always the probability distribution coming up from the product of many unknown factors. And this is precisely what happens in any civilization. We don't know how many factors played in the history of the United States since Columbus landed up to now, but certainly a number of them. So we can modelize that mathematically as an infinite number of factors, even if we don't know what the probability distribution is. Automatically, the log-normal distribution is the distribution for the time of the colony to emerge. Okay? So clearly there is a start, and then there is a peak, when the United States are still ruling the world, and then there is a peak down, and who knows who will be the next country. Sorry about that, I'm kidding, of course. But this is what the mathematics says, and if you pick up an history book, this is the story of all big empires. It's none of it. Incidentally, may suggest, please, to you an excellent book that really, I found it so lovely that I read it more than one time. The book is called Interstellar Migration and the Human Experience. You can find it in the web, but there aren't many copies available anymore because the book was published in 1983 and it was the proceedings of a conference attended by Jill Tarter, Carl Sagan, and other, probably from radicals, held at Los Alamos National Lab about the future of humanity into space. So it's a book, it's a qualitative book, there are just words, but it is so enlightening even for humanistically minded people, as I was, coming from a country that is supposed to do only art or something like that, right? It's really lets you read the history of the past in a new sense, which is the sense of SETI. For instance, that book handles the Greek expansion into the Mediterranean prior to the Roman conquest. And this is exactly what happens. They were hopping from one basis to another all over the Mediterranean coast. Also, it describes the colonization of the Vikings in medieval Europe, starting from Norway and so on, and finally they reached America. So again, they were hopping from one land to the next, which is exactly what is going to happen.
Polynesia.
Of course, thank you. Well, about Polynesia, may suggest another book, From Sea to Stars. This is the title, and I have to think about the author. But anyway, he's a professor at the University of Hawaii, and he describes just that 50,000 years were necessary for the Polynesians to expand across the whole Pacific Ocean, jumping from one island to the next. Please note that they did not know whether an island was really existing or not. They went up by trial and error, you know. So nobody knows how many people died in this expansion course, but this is what happened. So once again, also that topic could be cast in this mathematical mode. Look, I don't want to say much more. Let me just please shift to a different topic. Now you see this monster equation. Now, let me tell you something completely different from what I've been talking about so far. When a mathematician or a mathematical physicist wants to write down a model, of course the equations are very complicated. For instance, that thing, which is the probability density function necessary for any civilization to colonize the whole galaxy. Now, from the mathematics point of view, how can one possibly handle stuff like that without making errors? No, we are all humans. You know, the telephone rings and I have to stop the calculation, so I probably make errors. Well, let me confess what scientists do, but they are afraid somehow to confess it. I don't know why. I don't have any shame like that. Anyway, the idea is simply, we have to go over to a symbolic manipulation, like NASA's maximum and maximum. So I'm going to devote 1 minute to tell you this story, which is great. Please, when you go home, look at the web, and you may download Maxima with the X, this thing, for free. What is that? Well, that is a symbolic manipulator which I use to find this equation, capable of handling whole of mathematics, from differential equation to integral equation, tensor calculus requested for relativity, awful equation. You can handle that. And this was devised by NASA in the 60s, when they had to fly to the moon, and they had to be sure that all the knowledge piled up in the previous 300 centuries by mathematicians who were writing calculations by hand did not contain any error. This is mind-boggling. Now, as you can imagine, when NASA tried the book that they were using for the orbits of the moon, that is written by a French guy called Charles Delaunay, and in French that's Max like Théorie de la Lune, theory of the moon. Well, they found errors. So clearly, the creation of a code like that was necessary. There was no way out of that, and NASA did. So we now have other codes. I know we have Mathematica, we have Maples, very good things. But the first thing was that, and that now comes for free. So for the students or anyone who wants to do good research, I would not be ashamed to confess that I'm using Maxima, because since it has been used for 50 years, it is free from bugs, more than the recent codes. Okay? So I love that, and this is what I use in everyday's work. So, conclusion. First, statistics. Great, and all equations match perfectly, if you just take the logs. And then you apply the Central Limit Theorem of statistics. Good. Our Fermi Paradox statistical form is one consequence of that. Second, our mathematical theory also allows us to infer probability not only about us, but also about aliens. Because in the equation, we just have to change the characteristic of the planets of origin of those guys. And the mathematics immediately gives you, for instance, what is the average distance in between planets colonizable by those guys and not by us. So, This is particularly important in my opinion because the final goal of all this talk and my papers and my dream, honestly, that I hope will be taken up by some young people, is that we are already on the verge of writing a sort of Encyclopedia Galactica, as foreseen by Carl Sagan in his famous book and TV series Cosmos. What is that? Well, that is basically a large database with all the information we have about exosolar planets, stars. Of course, there are a number of stars. Let me just mention that here at the SETI Institute, there was, a few years ago, a conference about M stars. Now, what are M stars? M stars are those stars that are much more numerous than any other star. The Sun is a G star, so it's not of the most important type or the most populated type. But the point is that M stars may live billions of years. So clearly, a planet orbiting an M star has a higher probability than we have to develop life. We were able to do so in 4.5 billion years, but M stars probably are able to develop so in a shorter time, if the conditions are sufficient, of course. So the conclusion of my talk is this. What I try to explain here is the mathematical graph for developing a large code, also a database, automatically included, that would enable us to make predictions about stars, planets, living civilizations in this galaxy. And if this comes to become true, so it's a mathematical exercise, then my impression is that also the SETI searches that they do here, better than anywhere else in the world, could be influenced. Because the idea would be not just to explore everywhere, but to concentrate on those special kinds of stars that the computer code reveals as the more suitable for life, and search on those stars for extraterrestrial signals before we do so on other stars. Thank you very much.
We probably have a couple of minutes for questions. Could I ask one? You showed in your slides back here that you had a standard deviation. Oh, there could be too many slides. But of 200 million,
yeah,
plus or minus 200 million, and yet the number was about 100 million.
The planets, yes.
Right. Can you use that information to actually decrease your standard deviation at the front end of the equation?
Okay, now this is a profound question. Let me try to answer as best mathematically as I can see. All I described so far is just basically probability statistics applied to this kind of problem. But so far, I did not mention information theory, and in particular, Shannon's information theory and later. Now, information theory is the key to our current knowledge, especially computer sciences. We are in the place where Google is, so they know more than anyone else on earth about that. My answer to your question is that I have some idea about to develop information theory for those probability distributions. But at the moment, I did not write any paper. Essentially, there are, so as to say, higher notions that we have to bring in order to transform those probability distribution and the uncertainty or probability density information in the sense of Shannon into new variables that would help us to understand how much we know and how much we do not know. So this is something that is going on now, and I cannot say more.
With all due respect, I have a number of problems with your analysis, too many to discuss in this question session. But to follow up a little bit on Adrian's point, what you have here are probability distributions with a bunch of parameters in them representing the uncertainties of the various factors. And in one case, you pointed out that that meant quantitatively the distribution was meaningless. But doesn't that apply to all of your distributions? You don't know you have no a priori knowledge of the uncertainties of these underlying parameters. Another question, the Drake equation is actually a statistical equation from the beginning. It's a set of nested conditional probabilities, which you can estimate in some frequentist way. But so you're correctly saying let's understand the uncertainties in that factor, but you represent those as independent probabilities, and in fact they're nested conditional probabilities. So I don't understand that point.
Thank you.
Either, so.
Well, let me start with the second question. This is the same objection that Gilles Tarter made to my theory when he first presented here, so I'm aware of this. Okay, I don't know whether my answer will please you or not, but anyway, I tell you what I think, and I didn't have the time to work out in detail because this is all recent work, as you saw from the dates of the papers that they mentioned. Now, the question of dependence and independence is really a way to say that in the beginning, that is when you make the first investigation ever, you must assume that the variables are independent. Otherwise, you do not make any progress, which is what I did. Okay? Assuming that they are all independent factors, central limit.
But they're defined as conditional probabilities.
No.
They have a built-in dependence.
Sure. Now, at the moment, at the beginning, I assume that they are independent. However, of course, you are right. In the end, they turn out to be dependent. But the dependent stage is the second stage, not the first stage. And my point is that as long as science progresses, we come to understand the links in between these various probability distributions that in the first rough approximation we assume to be independent, but in reality they are not. The point is that the links were hidden in the beginning, so we could not immediately state what the dependency was and how much it was. So I don't know whether this pleases of you, but my one paper that I would like to write in the future is to go over to a larger theory that takes independence or dependence into account, starts by using independence, and goes up in finding hidden dependencies, which of course clarify the problem even better.
Just have one more question.
I would like to ask a really basic question. What are the units on the final number? Is it per year? Is it number of communicating civilizations per year?
No. Good question. It's the number of communicating civilizations right now, period. Now this may disappoint you, and of course you're right. But the time-dependent Drake equation has not been studied yet. You are right. We should go over to a time-dependent Drake equation. Of course. Would you do that, please? Yes. No, really, I agree. But then there are other questions. For instance, okay, I'm saying that because I see a number of young people in the audience. So you might wish to take up the challenge. There is no relationship between all is said and the theory of relativity. But in reality, of course, there is a relationship because the waves are traveling with the speed of light. So we certainly need a relativistic Drake equation. But who knows? You see, the point is that in 1961, Frank Drake gave the equation just for the fun of having an idea of how many possible civilizations there could be in the galaxy. And that is enough for that time. The point is that 50 years have elapsed, we know much more now, and so we need more. But again, there are large areas of science that are completely left out. And this, of course, is incorrect. We have to do it. I'm an old guy, you are a young guy, maybe you can do it.
Well, Claudio, we have a special memento of your
Wow.
talk, a very special talk for us here at SETI. So you'll all join me in thanking Claudio.
Thank you.